Hello everyone, welcome to RaveData, and in this video I will discuss sampling distribution and central limit theorem. So let's start with sampling distribution. Sampling distribution is a distribution of different sample statistics taken out from population. So please remember that statistic is a property of sample. In this case it is sampling mean. And let's say we are taking different sample from a population, and the uh, sample mean in the first sample is x1 bar, and second sample is x2 bar, and the third sample is x3 bar. So the distribution of all such sampling mean will be called as sampling distribution. So it is a distribution of different sample statistic taken from population. In this case, we took sample mean as a sample statistic. Throughout this lecture, I will use capital N for number of samples and N as sample size. Sample size, and N is the number of samples. So let's understand this using an example. Let's say we have a population with 3 data points. So there are 3 data points in this particular population, and the population parameter is equal to 2. In this case, population parameter is mean, right? So what we will do is we will sample it and take 2 samples from this population, and will repeat this many times. So in our case, N will become 2, and N is equal to, let's say, 1, 2, 3, 4, 5, 6, 7, 8, and 9. So our number of samples is 2 and the sample size is 9. So let's say we have these many samples, and the sample mean is, in this case, 1 plus 1 divided by 2 is equal to 1. And similarly, we took the sample mean of each and every sample. So now we will plot it. So you see that 1 and 3 appears only one time each, and 1.5 appears 2 times, 2 appears 3 times, and similarly 2.5 appears 2 times. And if you take the mean of this sample mean, so it will come out as, if you will sum it and then divide it by 9, so it will come out as 2. So see that the mean of the sample means is equal to 2, and the population mean was also equal to 2. So these things you keep in mind. Let's plot this thing. So you see that on y-axis is the frequency, on x-axis we have sampling mean. So 1 comes 1 times, 1.5 comes 2 times, 2 comes 3 times, and 2.5 comes 2 times, and similarly 3 comes 1 time, as per this table. So, and the mean of this sampling distribution of mean is also equal to 2. So we will have very important inference from here. This simplest sampling distribution shows that most of the times the statistic, means sample mean in this case, correctly identifies the parameter, that is population mean. And if you will connect these dots, you see that it follows a triangular kind of shape, because here N was 2 and N is equal to 9. In the next slide, we'll see that if N is greater than 30, means the sample size is greater than 30, then the sampling distribution follows a normal distribution, and we call it, this theorem, as central limit theorem. Let's move on to central limit theorem. The central limit theorem states that as the size of the sample increases, as a thumb rule, and should be greater than 30, the distribution of the means across multiple samples will approximate a normal distribution. So we can have population mean of any shape, means it can be of this shape or this shape or any shape, but the distribution of sample statistic will always follow a Gaussian or normal distribution. So in our case, the sample statistic is sample mean. So there are few prerequisites of central limit theorem. First is sampling must be randomly executed. Samples must be independent among each other, and the sample size should be sufficiently large, say greater than 30. And if the sample size is enough, central limit theorem will hold for any distribution of population. And we can approximate the population mean. Population mean is usually unknown, and we try to approximate it. So we can approximate the population mean with sampling distribution means. Like if the mu is unknown, we do not know mean, then we can say that mu is equal to mu x bar, means the mean of this sampling distribution. We can approximate it, and it is found that this is fairly good approximation. So I hope you understood the central limit theorem, but I will move to a animation so that you understand it intuitively. So let's move on to an animation. I will share this link with all of you in the comment box. So here in the first graph, the parent population is given. That is the population from which we are sampling. So let's assume that the parent population is a skewed distribution. And you can see that the mean of this parent population is 8.08. So what we will do is we will take samples from it. And let's say we are considering the sample means. So let's take 10,000 samples of, means sample size as 10,000, and we will take the number of samples as 5, and we will take the sample size as 10,000. So you can see that here n is equal to 5, and the sample size we took as 10,000. So you see that the sampling distribution follows a normal distribution in both the cases, because the n is equal to 5 in both cases. Let's say in the second case we assume n is equal to 25, and then we'll sample it. So you see that in first case the number of samples is 5, and in the second case number of samples taken is 25, and the sample size is 10,000 in both the cases. So you see that the sampling distribution follows a normal distribution in both the cases. But as the number of sample increases, the standard error decreases. We will discuss standard error later in this video. And if we further increase the sample, let's say we do it 100,000 sample, then you see that the normal distribution approximation increases. And let's see the mean of this distribution. So you see that the mean of this distribution is 8.10, and the actual mean is 8.08. So it approximates the population mean. And when the number of sample increases, the distribution mean is exactly equal to population mean. And this is what central limit theorem tells us. So let's go back to our slides. I hope the central limit theorem is clear to you. So we'll next move on to the central limit theorem example. So in this example, what we have taken is we took a rolling dice example. This has 6 outcomes between 1 and 6, and all outcomes are equally probable. Let's our population is the frequency of outcomes when a dice is rolled 10,000 times. Each instance of rolling of dice is independent of the other. Let's our sample is the mean of outcome when a dice is rolled 50 times, means here n is equal to 50. And let's repeat this process 1,000 times, means sample size is 1,000. If the mean of those samples are plotted, it approximates normal distribution. Here it is plotted, and we have seen this using animation also. That's it. This holds. Now let's move on to standard error. So standard error is nothing but the standard deviation for the distribution of means. Means this is the sampling distribution, and the standard deviation of this sampling distribution is called standard error. And you see as the number of sample increases, the standard error reduces. as n increases, standard error reduces. So I have just showed you in the animation earlier. So it tells us how far does the sample statistics deviate from actual population mean. If the population standard deviation is known, then the sample standard error of the mean can be calculated using this formula, sigma divided by root n. And remember that n here is the number of samples, means you should take it as n, sigma divided by root n. From the last figure, it seems intuitive that if the sample size increases, the standard error reduces. You see that as n is increasing, the standard error, this boundary is decreasing. You see in the first case, the standard error is 3.99, and in the second case, it's become 1.80. So let's revisit what we have studied so far. We studied sampling distribution, what is sampling distribution is. Then we took an example of sampling distribution, and then we said that as the sample size increases, the sampling distribution follows a normal distribution. And then we went on to see a animation for this particular theorem. And then we studied standard error, and we concluded that as the number of sample increases, the standard error reduces. So I hope you like this video, and if you have any doubt, you can write in the comment box, and you can subscribe to our channel so that you don't miss out other videos in the same series. Thank you.